Hello, my name is Erfan Arefin, and I will be presenting our paper, Deep Neural Exposure You Can Run But Not Hide Your Neural Network Architecture. This work was done by myself and Dr. Abdul from Texas Tech University. So we'll be focusing on neural network security. Neural networks are basically a series of algorithms that mimic the operation of a human brain. It has interconnected processing elements that we call neurons, and when we feed some data to it, it generates its own understanding, which we call features. And this can be used in various applications, such as the financials. It can be used in financial services. It can be used for fraud detection. It can be used for image recognition, image classification. It can even be used for landing robots on Comet. So there are like many different types of neural networks out there, and we'll be focusing on convolution neural networks, which are CNNs. So we have an attack scenario here. So we assume there is an application, an AI application, which is running on a laptop. So this AI application was developed by some company which used some sort of neural network, tuned it and optimized it on its own way based on the needs of this application. And that neural network architecture and the optimization and the key features are the intellectual property of that company. And they have secretly, they have guarded that, and which is basically a secret, and do not want that to be exposed, because that's what makes this application very unique, and that's why customers use it. So if a customer is using this on a laptop, and maybe it's processing some sort of image or maybe audio or maybe a video, and it's running on the GPU, because most of the neural networks runs on GPU. And when it's running on the GPU, it generates, it draws some significant number of power, a significant amount of power. So that's where we're going to focus. So we have an attacker here that feeds malicious inputs to this application and monitors its power so that it can find some sort of pattern to figure out and mix and match with other patterns of other neural networks to figure out what architecture and what key features does this neural network uses on this AI application. And that's how we try to expose certain architectures in our attack. And we get this power data from the GPU, and then we do some sort of feature extraction on it, and then we further classify. And that's how we reveal the underlying neural network that's been used by this AI application. So I'm going to talk about ImageNet and one of its competition. So ImageNet Large-Scale Visual Recognition Challenge, or in short ILS-VRC, it's a competition that evaluates algorithms and object detection and image classification at large scale. So many research labs and companies try to develop different sort of architectures, different sort of CNNs, and they have been coming out in different years by this competition and also some other conferences. So we went to their website and found all these architectures, and we used that. There are like other many different architectures available. I just mentioned a few here, and we use that in our research here. So before we dive into the attack, I want to explain why the architecture is important, because we have an example architecture here, which is VGG16, and this CNN architecture uses 3 fully connected layers, 13 convolution layers, 5 pooling layer, and 1 softmax layer, all organized in a certain way. And this number of layers and their organization makes this architecture unique. Now let's have a look at some other architectures. So there's an overview, a comparison of CNN architectures here. We have 10 architectures here, 10 CNN architectures here, which have different number of convolution layer, fully connected layer, and pooling layers. They have different number of total parameters. They use different amount of dropout in different ways, and that is the key feature of our attack, because since the layers are organized in a unique way, and the number of layers are also unique. They consume a unique unique amount of power when they are fed with the same image to classify. So they generate some sort of power signature, which is unique to classify that what architecture is running on the GPU. So we used GPU-Z software, which was developed by Take Power Up, and this is used. This is used in many other ways, but we use that to log the power consumed by the GPU. So it can produce 100 samples per second. It's a very good sampling rate for our work, and we can and it can read the sensors, the power sensors of GPU. So we used an NVIDIA RTX 2060, and these are the sensors that were available on this GPU. So this software generates a log file, and it has all the timestamps and the sensor values on different rows. So we use that log in our research here. So our implementation is quite straightforward. We did not train any CNNs because training CNNs is a very resource-hungry work. So we use pre-trained CNNs. So these pre-trained CNNs have checkpoints on their servers so that it can be just used out of the box. And PyTorch provides pre-trained CNNs, and we use Python to implement our experiment. We basically fed a number of images to all the architectures here, and we recorded its power consumption pattern, and later we extracted feature from it to feed that to classifiers to figure out that what architecture is actually running. So we used tsfresh library to extract feature, and here's a summary of all the features that has been extracted from these sensor values. This is a very simple 2D plot. On the x-axis we have auto covariance of power GPU chip, and on y-axis we have absolute energy of power GPU chip. And I have plotted only 4 networks here just to show an example, just to visually give you an idea that all the power consumptions for these 4 architectures are even visually distinguishable. So we use 2 different datasets in our research here. Dataset 1 uses cats and dogs. There is 50 samples of cats and 50 samples of dogs here. The reason is commonly cats and dogs are quite misclassified, and different breeds of cats and different breeds of dogs makes this dataset samples quite similar. And dataset 2 we use totally random images. The reason of this selection of datasets is because we wanted to see the power signature of these 2 different datasets. So if you fit similar images, similar layers should be triggered, and similar amount of power should be consumed. And if you feed different type of images, that is different layers would be triggered by the CNN architectures, and different power signature will be generated. So we test the 10 basic CNN architectures that we showed on the comparison table, and we fed all those images, all dataset 1 and dataset 2 to record the power data, and also then we extracted feature from it, and we ran 2 classifiers here on the extracted features. We used random forest and logistic regression here, and you can see that dataset 2 performed well compared to dataset 1, mostly because dataset 1's images were very similar to each other, and thus they generated similar power signature. So it was hard for the classifier to classify them. But for dataset 2, it was not that hard. So thus it has a better average accuracy. So now I'm going to talk about the attack configuration, and before I do that, I want to focus on some variants of the CNN architectures. So among those 10 architectures, these 7 architectures have many different variants. We focus on this variance because many AI application can use different variants of those CNN architectures based on their needs. So we also considered this in our research. So we have three different attack scenarios here. Attack scenario 1 is pretty straightforward. So we assume that the attacker has access to the power data of the 10 core CNN architectures, so that the attacker trained its classifier with this data. And when it gets the data, when it gets the power data from the victim, so that it can just feed it here as testing data, and can figure out what architecture is the victim is actually using. And for the second configuration, we assume that the attacker has only access to the core CNN architectures and does not have access to the variants. So if the victim is running some sort of variant on its laptop, so and if that power data is collected, how will this power data be classified? That's what we explored on our attack configuration 2. In our attack configuration 3, we assume that the attacker has the data, the power data, for all the 32 variants, and so that when the attacker gets the data, the power data from the victim, it can just feed that to its classifier to see what variant the victim is running. So we ran random forest here, and we used only dataset 2 because it performed well in this research. So attack configuration 1 have the highest average accuracy, and attack configuration 3 has the second highest accuracy, and attack configuration 2 has the least average accuracy here. And we can assume that the first one's accuracy is far better because it's a 10 class problem, and when we focus on the third one, it is a 32 class problem. And when we focus on the 2, or attack configuration 2, it is also a 32 class problem, but the training data was not that much significant because it had only access to the 7 core architectures, the power data of the power data of the 7 core architectures for training. So this was our presentation. I hope you liked it. Thank you very much.